I'm from the Energy Futures Lab, and this is one of this Materials for Energy paper that we'll be presenting is one of our Energy Futures Lab briefing paper series. The Energy Futures Lab is an institution of Imperial College London, and our job is basically, it's a few-fold. It's to connect the various energy research teams at Imperial together, enabling people to sort of cross-pollinate and understand what everyone else is working on, to present a sort of public-facing side to the Imperial's energy research capabilities, so a single point of contact for outside stakeholders interested in working with us, and also to provide policy inputs in the form of both consultation responses, direct meetings with policymakers and politicians, and also longer form pieces of work such as our briefing paper series. These are 4 of our earliest briefing papers. We've had several more since then. And the idea is basically to look at a sector of energy research or interest at this moment and look at it in a kind of rigorous, neutral way and present that in a sort of policy focused way so policymakers can both read it and understand it. So it's not written in academic lingo, it's written in relatively easy to grasp language, and with policy recommendations for people to directly take forward. So this piece of work we've been working on for about a year and a half, on and off, and we're nearly ready to publish it. We will be publishing it towards the end of this year, month. So, and this is basically a kind of early look at what we're discussing in the paper, and you'll be able to download the full paper towards the end of this month, and we'll send out a link when it's available. We've also done this work in conjunction with the UK Energy Research Centre. So Phil and Jamie are researchers in the TPA function of the Energy Research Centre, UK Energy Research Centre, and they will now take over and explain to you more about UKERC and what it does. So let me give the control to Phil.
A very brief overview of what the UK Energy Research Centre is. It's a sort of virtual centre that's made up of, well, more than 20 institutions across the UK. And it's been in existence since 2004, now in its 4th phase, funded by the, well, originally funded by the Research Councils and now funded by the UK Research and Innovation Energy Programme. And the job of UKERC overall is to provide the sort of, if you like, a home for energy research across the UK, and to focus on those challenges which the UK is going to face in terms of its energy transition and its transition to net zero. And the bit of UKERC that myself and Jamie are part of is called the Technology and Policy Assessment Function, and that's been part of UKERC since its very start. And the job we have in the TPA team is to carry out systematic reviews of contentious issues in the energy policy space, and we've been doing that, as I say, since 2004. The reason we're involved with this project and working with EFL is because back in 2014, Jamie and colleagues looked at the materials issue and wrote a report, a full TPA report, of which Jamie was the lead author. And this was a great opportunity for us to revisit some of the issues which were raised by that report, and to see how the story had changed, and what had changed, what hasn't changed, and what the issues are for policymakers going forward. So that's UKERC. In terms of the project overview, as I said before, it's a joint effort between the Energy Futures Lab and the UK Energy Research Centre, and the project is split into 3 parts, and this presentation follows those 3 parts. Part 1 is what Jamie and I will be talking about, where we present 4 case studies of materials that we think, well, everybody thinks will be critical to the transition to net zero, although one of them might be not as critical as some may have thought. I'm going to explain that in a moment. The second two parts which Aidan will lead on, they will look at the state of development of novel materials in the UK energy sector. And part three, in part three, Aidan will talk about the results of a workshop that he undertook earlier this year, talking to a range of stakeholders about what they thought the challenges that facing the development of novel materials for the energy sector are. So that's the overview. So moving swiftly on to part one, the case studies. So as I say, we selected four critical materials. Now we're not suggesting for a moment that one can think that critical materials for the energy transition are homogeneous or also share the same characteristics, but there are some shared characteristics and some shared some things which sort of generate a series of shared themes, if you like, and I've listed them there in the third bullet point and the sub bullets. And it's in colloquial terms, that what that translates into is how much is there of the particular resource, how much do we think we're going to need of that particular resource out into the future, and how good are we, and how likely are we to be able to actually physically dig the stuff out the ground and process it and produce it and get it to where it needs to be in the right time. And then finally about what the implications are for recycling. And the four materials we've chosen, and we're going to cover them in this order, are lithium, copper, tellurium, and cobalt. I'm going to cover lithium, copper, and tellurium, and I'll explain why we've chosen those three materials as we go through, and then Jamie's going to cover the fourth material, cobalt. So the first one, case study is lithium. As I'm sure most of you, if not all of you, know, a key material in batteries, and what's driving or what will drive the future demand for lithium, and certainly the massive increase in demand for lithium in the future that's projected, is the demand for batteries for the electric vehicles and in the stationary power market as well. That's providing some resilience to electricity systems. That's where the stationary market's coming from. And what we're showing on this chart is the production levels for the last 10 years, the reserve levels, and the fundamental resource level as well. And I think that perhaps just the overall, by the way, this data and the data for all the other materials comes from the US Geological Survey. So I suppose the message for this chart is that the current production levels of lithium are only a tiny, really tiny fraction of currently determined reserves, and an even smaller fraction of currently determined resources. But that doesn't mean there's not necessarily to be concerned about or issues to be at least to be aware of. So this slide just summarizes what we believe is the case in terms of lithium. So it's fairly clear, in fact very clear, that the current reserves and resources of lithium far exceed the existing demand. And we did a systematic review of the projected demands for these materials, and we found that even the excluding one or two very, very unusual outliers, the projected demand for lithium is well within the projected resources over the next three or four decades. However, the current production capacity is significantly constrained, and there is you can see a lot of more activity in the development of lithium mining projects, lithium production projects. But it is almost certainly the case that the very tight supply market that we've had over the last year or two is likely to sustain simply because it takes so long to develop these projects. Also, this has been in the news quite a lot, and obviously what with current situation in the Eastern Europe, there's a lot of issues and concern around the concentration of supply of energy resources, and lithium is one of those materials whose supply comes from a very, very small number of countries, and also the production supply chain is very geographically concentrated as well. well. And there's also very little recycling that takes place currently with lithium, but there is quite a lot of evidence to suggest that that recycling could be ramped up quite considerably and could make a considerably bigger contribution in the future. Next material up is copper. I mean, I'm sure you're all aware of what we use copper for, but essentially it's very, very widely used in electrical, both electrical components, electrical machines and what have you, and in electricity industry. And it's very, very relatively common element, relatively abundant. But in many ways, it's a similar-ish story to lithium in that the current production levels are a very, very small component of both reserves and resources. And that's been relatively sort of stable throughout the last sort of 10 years. The dip in resources in the 2013, it was the way USGS changed the way in which they measured it for 1 year, so it can be largely ignored. However, there are some interesting things about copper. First off, it is, as I've said, it's abundant, easily recyclable. And although recycling levels are relatively high because of that, there is still quite a lot of headroom in terms of how much more we could do in terms of recycling. Very interesting in that despite a considerable volatility in the copper markets over the last multi-decades, really, it has proven very, very resistant to substitution by other materials, and that's partly because it is so readily available to some extent, but also it is very, very good for what it's used for, and some of the other potentially substitute materials are either not as good or significantly more expensive. Future demand is forecast on almost any measure to increase very, very substantially. And if you look at the very, very highest projections for that future demand, we get to a situation potentially where some of the resources may get to the point where they are being exhausted. But I'd stress that that's at the very highest end of the range of future projections. However, in the sort of shorter term, copper faces the same problems affected by a lot of extraction industry. In the investment in production facilities is very cyclical, and those sort of market dynamics are expected to have create some bottlenecks for the sort of near-term and medium-term future demand. Now, so next up for me is Tellurium. Thank you, Jamie. Now, Tellurium is a really interesting one, actually, which is why I'm mortified that I've forgotten it. Because Tellurium, and the eagle-eyed amongst you will notice that there are no resource levels shown for Tellurium. That's because it's essentially produces a byproduct of copper production and refining. So there aren't any USGS data for resource levels. But you've got in many ways, you've still got a situation where production levels are a very, very small component, or a very small fraction of known reserves, sorry. But it's an interesting example, and perhaps not for the reasons that you might think. I'll just try and go on to the next slide here. Okay, so the reason we think it's interesting is because if you go back about a decade or more, and bearing in mind that what I should make it clear that the reason why we're interested in Tellurium is because it's a key component in thin film photovoltaics. Which a decade or more ago were considered to be the sort of up-and-coming technology for photovoltaics. And there was a very widely held view, actually, that thin film PV would potentially come to have a, maybe not dominant, but certainly a very, very important role and share of the global PV market. And the estimates for future Tellurium demand at that point, so going back 10 years, what estimates were for out into the future, reflected that optimism around thin film PV and what that would mean for Tellurium demand. Some of those projections concluded that the future demand for Tellurium would or could potentially significantly outstrip both production and total reserve capacity in the medium and long term. And those concerns were exacerbated because, as I mentioned a moment ago, the Tellurium is produced primarily as a byproduct of producing and refining copper. What happened in practice is that the thin film PV did not make the sort of market inroads that it was expected to do. So the sort of demand for tellurium has not moved in the direction that was anticipated or that was forecast, and unless there's any huge change in the sort of relative cost and advantages of thin film versus crystalline PV, there's very little evidence suggesting that that's a situation likely to change. So we've got a situation here where we had a material whose future demand was projected to rise very, very quickly, and to the point where it could start to approach known resources, known reserves, but that did not happen. So we think that's a really interesting example. And I think that is me now, isn't it, Jamie? You know, yep.
Yeah, I think you're done now. Thanks for your last two slides. So I'm going to give you a brief overview of Cobalt before and going through some of the summary points for this half, and then hopefully if there are any questions for us, we can deal with them before moving on to the second part. Cobalt is a very similar figure to the ones that Phil showed for the previous materials. Cobalt is very similar to tellurium in that there are no resource estimates here, because similarly cobalt is largely produced as a byproduct of copper and nickel mining. And there are some dedicated primary production routes to cobalt, but mostly the majority of the market comes from these secondary sources, which creates those types of difficult supply side dynamics that Phil alluded to. And again, there's a very similar story here in terms of the proportion of production to what we know are reserves. Reserves have been relatively flat over the last decade, although slightly declining. But between 2020 and 2021, estimated reserves increased to slightly over the levels in 2011. So that's 7.5 million tons in 2011 to 7.6 million tons in 2021. So relatively flat, although showing a rising trend in recent years, and that's largely in response to price dynamics of cobalt, because cobalt is similarly tight supply market to the one described for lithium earlier. Production is also increasing, and cobalt is used primarily in the current market for electrode chemistries in lithium-ion batteries. So it's subject to the similar demand side dynamics that lithium is. Something like 65% of the cobalt market is in batteries. That's again across consumer electronics, electric vehicles, and to a smaller extent, although growing at the moment, in stationary storage applications. Electric vehicle applications actually just overtook consumer electronics in the last couple of years as the dominant demand in the battery market. And as you would expect, that is the key area of the market that's expected to drive significant amounts of growth. Historically, cobalt was used as an alloy in magnets and as an alloy in superalloys, so alloyed metals designed to have very high tolerances to specific conditions. So just to capture some of the things that we think are interesting about cobalt and why we're looking at cobalt. Cobalt availability has experienced very measurable market constraints in the past. And it's therefore, I think, a good example of what things happen when material supplies become very tight. And it gives us a historical reference to examine. And the reason that cobalt experienced supply constraints was driven by kind of key characteristics that we think are important in material availability. It's very geographically constrained. A very large proportion of production comes from the Democratic Republic of Congo. And that has been the case for the majority of the modern market for cobalt. In the late 1970s, political unrest in the country led to difficulties in shipping cobalt and a reduction in production levels. And that had a very significant impact on the price at the time, which spiked very significantly. And given that it's a secondary metal that is produced as a byproduct of other metal recovery, it's very difficult to change dynamically in the short term production rates in other parts of the world. So that was a significant challenge for cobalt. Interestingly, that example encouraged significant investment in innovation around alternative materials. One of the key uses, as I mentioned, was in high-strength magnets at the time. And that led to the development of alternative chemistries, alternative alloys for high-strength magnets, one of those being neodymium magnets, which have now become the main high-strength magnet alloys, and is an example of where substitution has been successful in being used as a response to supply constraints for a specific material. Future ability of cobalt is still of concern, because despite the ability to substitute in other uses, it's proved to be quite sticky in terms of still being one of the best, a component of one of the best types of lithium-ion chemistry. There are other lithium-ion chemistries that reduce or remove the use of cobalt, but cobalt is still in a significant proportion of lithium-ion batteries produced. And as Phil alluded, the battery market is likely to grow significantly, and that's going to drive cobalt demand, given the extent that lithium batteries play in the demand side for cobalt. It's not particularly well recycled at the moment, and as I've just said, its substitution has been challenging, and so it's definitely a metal worth keeping an eye on in terms of what may happen in the future. Okay, so to sum up quickly, there's a very wide range of demand forecasts over really long timescales, and that is obviously quite challenging in terms of examining what might happen in the future for these critical materials. Fundamental resource availability, so running out of, in inverted commas, a metal or a material, does not seem to be a primary concern in the majority of the literature, save for a few small outlying reports that raise alarm bells about that, particular issues around resource quantities specifically. Concern in the literature seems more predominantly to be around rates of extraction and production and recycling in the face of what future demand might look like. And as we've tried to highlight, for some of these materials, the market dynamics don't simply respond immediately to price signals, because a significant factor in the rate of recovery is the rate of recovery of the associated primary metal that these are produced as byproducts of. So that's a very complicated dynamic that definitely gets in the way of simple supply and demand balancing around a price signal. Another thing is that to investigate and bring online new projects through exploration and production has long lead times. And so that's, although there are resources for some of these metals in parts of the world that aren't currently produced at scale, those can be brought online, but not in the short to medium term in many cases. The demand side obviously shows for many of these materials critical for the transition to a low carbon economy, shows a significant step change in terms of demand. And that is, I think, one of the key reasons driving concern about these materials, that we're in the foothills of a new era of demand for many of these materials. And that obviously raises concern and initiates a lot of the studies that examine this issue. Supply of those materials, again, whose production is as a byproduct, as I've said, is a key issue. And so identifying which of those materials are byproducts is a key part of any of these analyses of multi-materials and ranking of criticality for these materials. Geographical concentration, again, another thing that we've tried to highlight here. A number of these materials are produced in the majority of these materials produced in a small number of countries or geographical locations around the world. And that brings into play geopolitical risks associated with production. Yeah, there's a point here about the evolution of dominant technologies in some sectors, and dramatically revising demand forecasts. That speaks specifically to the tellurium issue that Phil highlighted earlier. Of course, where markets don't evolve, and in some respects that can be seen as a substitution issue, where you have competing technologies. Projections for some of those technologies might be quite optimistic at one point, and then be revised significantly due to changes in technology development and other substitutes. And so where some materials might look to be potentially constrained in the future, at one point, the evolving story around those technologies that are driving demand might end up telling a different story over time. We've included a couple of points here around what are the levers that one might pull if you were trying to design industrial policy or trying to mitigate against some of the issues that we've highlighted. And there are relatively few, given that often these issues are around global markets with very few players. It can be quite challenging to mitigate against these issues. But some of the things that we've highlighted here are, for example, to where constraints are identified, to try to grease the wheels, as it were, of the development of new projects, to try and minimize that lag time that we've discussed. Another area is the issues around rates of production, refining, and the geographical concentration issue. And again, here there are relatively few things that a company who requires these materials or a country who's strategically interested in worrying about these things. But for example, stockpiling and developing inventory for things that a given country or company are concerned about may be one way in which these issues can be mitigated. Another one that we've not highlighted there for companies specifically is vertical integration, which has happened at times in the PV market, where acquisition of mining companies by the users of those materials might be a way of getting a better understanding of the dynamics of supply to plan business development better. And the final one we've got there, which I think is always a good idea, is to review forecasts over time. As again, we've highlighted, this is a very dynamic issue. Things change dramatically over time. You know, whilst we have highlighted an issue where a material might have become less concern over time, the inverse is also potentially true, that new materials might suddenly become significantly more critical, depending on the way in which these issues develop over time. That's everything from me. I'll hand back to Aidan now, but I'm not sure if Aidan is covering the Q&A and if there are any specific questions that I'm answering now before I have to disappear.
So we've got a couple of Q&A questions in. Right, there's one, well, there's two from anonymous attendees. So let's start with the first one. Is Should we be worried? You should be able to see these in the Q&A thing yourself. Should we be worried about human rights and supply chains for these materials? Are we making the same mistakes in the clean energy transition as we did in the past, when there's a lack of responsibility shown by fossil fuel companies, resulting in native citizens not reaping the rewards of the resources available? Either of you have a comment on that?
Oh, I mean, the first thing I think is worth saying is that we haven't looked at all at issues of human rights or other environmental issues around mining extraction. I think those are both really valid questions and concerns, and we don't look at them here. Of course, there are many historical examples where extraction industries have got these issues wrong. It is, however, necessary, if we want availability of these materials, to maintain extraction practices in the future. And I think it's incumbent on the regulators and those involved in those practices to make sure that those issues are dealt with. But again, we do not deal with those issues in the course of the report, but they are very much worth asking. Phil, I don't know if you want to add anything to that.
I don't think I can add a great deal to that. I think there is at least one question about thin film PV in respect to Tellurium, Jamie, which I think you're better placed to answer than I am. So would you mind jumping into that one?
This is the one. Yeah, this is from Professor Gross.
Yeah.
Do we know if Tellurium availability or price had any bearing on the failure of cadmium telluride panels to break through into the mass PV market, or was it just literally that Chinese manufacturers got onto it and the incumbent technology just got better and better and better? He also sticks on an addendum about cobalt. Like I said, explicit efforts were made to substitute in cobalt instead of tellurium. What's going on? So
I think it would be hard to distinguish between the influence of any of those factors. I think it's all of them to varying extents. So CAD-TEL was a thin film technology. It was going to be probably less efficient than silicon-based alternatives, but potentially much cheaper to develop, and potentially can be incorporated into different functional forms, so you could use it much more easily in building integrated type PV technologies. What happened really is what happened to CAD-TEL really is what happened on the crystalline silicon side of the market, and as prices were driven down by Chinese manufacturing, the argument around cheap CAD-TEL was eroded, and the differential between the prospects for the price of CAD-TEL versus crystalline silicon was minimized, and that definitely ate into the demand side for CAD-TEL, or the growth of CAD-TEL into the market. Whether that's a win for crystalline silicon development or a failure of CAD-TEL to keep up with those types of price reductions and to develop quickly enough, it's hard to say. Comparing cobalt, I think that for substitution, so specifically, I think Rob's question there on cobalt in comparison is that cobalt's been okay in inverted commas because some of the substitution moves made away from other cobalt uses. With the substitution story is always very technology specific. Sometimes it's easier to find a way out of a material use for some technology applications than for others. And I don't think it's easy to say where substitution will be easier and where substitution will be harder. I'm not sure I can add much to that. It remains to be seen whether we can effectively substitute cobalt in lithium-ion batteries without significantly affecting the utility of those batteries, because at the moment there are definitely trade-offs in getting rid of cobalt from lithium-ion batteries, which is why cobalt is quite sticky in lithium-ion chemistries for the time being.
Okay, and just a couple more questions, both of which I'll stick together, one from Anonymous and one from Catherine Jackson. What do you think about the argument that the amount of resources required for these new techs, EVs, PVs, means that these projects aren't green? How do these volumes compare to fossil fuel extraction? Another one, sort of related, but do you find any issues in literature about ecological impact and damage and the constraints that these could put on the ability to extract these resources?
I'll take the second one of those, if you like, Aidan.
Yeah, go for it.
And it's only a partial answer, I'm afraid. When I was looking through the literature on demand projections, sort of out into the future, there was a subset of those analyses that did explicitly consider the ecological impacts of very, very high levels of resource extraction for some of the resources that we're going to need, and several of those analyses did flag up that as a potential issue. It wasn't the focus of our work, but it certainly is the case that several of the several analyses have flagged that up as a significant potential issue. Yeah. As far as whether or not electric vehicles are green or not, that definitely wasn't part of the research that I was involved in. I suppose it all comes down to relatively, speaking, yeah. But it wasn't part of it wasn't the research question we tried to answer, I'm afraid.
Okay, brilliant. Well, thanks, Jamie. I know you have to drop off.
Thank you.
So we've got about 20 minutes left, so I will rush through my sections. So I'm going to do two sections today, one looking at novel functional materials in a technology aspect, and one looking at the results of a workshop on what we can actually do in the UK to push forward sort of research and policy recommendations to improve our novel materials development chains. And so this section on novel functional materials I will go through relatively fast. There's a lot more evidence and stuff basically written in the final report in this area, which will be coming out towards the end of October, and it was developed in conjunction with the Henry Royce Institute, which is a large virtual materials institute spanning several UK universities, and they have published some excuse me, they published some roadmaps for the UK novel energy materials landscape, which you can find on their website, and goes into some of these areas in a lot more depth than I can do here. So novel materials are basically some of these materials that we already use aren't as good as they could be, or a lot more scarce than they could be, or a lot more expensive than they could be. So basically, can we improve the characteristics of our current energy technologies by substituting existing materials for developing ones, or can we develop novel materials, get current actors replacements for these existing materials, which could be either very scarce or expensive, stuff like platinum, for example, in fuel cells, or as we've seen in some of these materials, like are associated with large amounts of ecological and environmental damage. So I looked at three sections for this, three technology areas for this specific report. As I said, these correspond to the materials for the energy transition roadmaps, which you can find on the Henry Royce Institute's website. Photovoltaics, batteries, and materials for hydrogen and other energy carriers. So I've already had a bit of a chat about solar PV already in this, but as pointed out, solar PV is currently dominated by crystalline silicon. It represents something like 95% of the market, and most roadmaps nowadays think the crystalline silicon is likely to remain the established technology until at least the 2040s due to its low cost and constant improvements in amount of resources it actually uses. It doesn't mean there aren't some research challenges to make silicon PV better. Reduction of silicon to silver intensities, making them thinner, making them lighter, making them less silicon to silver, both relatively expensive, especially good quality crystalline silicon. So the less of that you could use in a PV panel, the better. Reducing the heating reducing the heating on the panel as solar PV gets less efficient as the panel heats up, and obviously they're in direct sunlight, so ways to deal with that, and also ways to deal with panel soiling when dust, dirt, leaves fall on them. In terms of established competitor technologies, thin film PV is the most established one of these, as we talked about, but it really hasn't maybe met the ambitions that we saw earlier on in the decade in terms of market share Part of this is efficient scale up, ability to manufacture large quantities. Tellurium availability, that was seen to be a problem if we were going to scale up massively. But now, as we've seen, Tellurium forecasts have dropped significantly, and also recycling chains. You can see on the right hand side a classification of solar cell technologies, and on the right hand side you can see a series of emerging and novel materials. This is what they call third generation solar panels. These consist of several technologies: organic PV cells, quantum dots, perovskites. That's a perovskite molecule there on the right. Dye-sensitized cells, multi-junction cells, other sort of cells. These are all covered in much greater detail in the report. Most of these technologies are either at the very much the pre-commercialization stage, so late demonstration or the R&D development. They are, however, do show some useful abilities. They tend to be lighter weight than the solar panel silicon technologies. They could well be easier to manufacture with lower costs, and they are more suitable for a wider range of use cases. So you could integrate these onto buildings, onto windows, onto roofs in a lot more integrated way than current silicon PV, and also they're much more suitable for indoor and mobile uses. But there are significant challenges in commercialization for these novel PV cells. The first one is degradation. A standard silicon PV cell lasts roughly 25 to 30 years, we think of working lifetime is at the moment. Whereas a lot of these technologies, once again talking about perovskites, can last only a year or two in sort of standard conditions of sort of outside external environmental conditions. So these degradation issues need to be fixed. Materials availability and toxicity is also an issue, especially once go with perovskites, because they often at the moment contain lead halide compounds, which are extremely toxic. Sustainability and recycling, how we actually recycle these materials. If we're going to develop net zero value supply chains now, we need to think about developing sustainability recycling into the process as we actually develop the initial commercialization aspects. And finally, just developing and scaling up manufacturing processes. These require significant infrastructure and capital requirements, and the danger is, of course, that you have a very successful incumbent technology in the form of silicon PV, and investors will be thinking, why should I invest more money in this when you're unlikely to be able to catch it up for a decade or more? So in the UK, we have a relatively good sort of basic to advanced R&D capabilities in new PV in the UK, but we are missing significant demonstration test beds, especially in degradation and stability, in order to basically demonstrate that these technologies are fit for commercialization and can actually withstand environmental conditions. So that is one major recommendation. Basically, the UK as a whole has an issue with taking technologies from the R&D stage to the demonstration and commercialization stage. And in the case of these PV technologies, degradation and stability test beds are important. Moving on swiftly to batteries. Batteries, of course, are essential components of the clean energy transition. They are super important for everything from electronics to electric vehicles, and also grid scale and domestic scale energy storage. The preeminent battery technology used today is, of course, lithium ion. It's pretty good, it's pretty affordable, it's relatively high density, and comparably to other technologies, it has decent lifetimes and high cycling efficiencies. However, there is increasing demand for higher energy densities than we can get with lithium ion batteries. These come from both the electric vehicles. Obviously, higher energy density means higher range, and also electronics, because higher energy density means a longer lifetime on your mobile phone. And really, lithium ion has kind of stagnated as a technology over the last decade. It has got a bit better, but not dramatically better, and there's definitely got a lot slower than the evolution of, for example, mobile technology. And a lot of this is just basically because we need better chemistry, which can give us better energy and power densities. So these novel battery chemistries. I've looked at significant lithium related ones, lithium sulfur, lithium oxygen, lithium organic, and also solid state lithium battery cells. And these are battery cells without significant liquid electrolyte in them, which should be lighter and safer. There are also other chemistries, including magnesium and sulfur batteries, which are being looked at again. But lithium is extremely well understood molecule with extremely well understood properties. This has been a real sort of, there has been a huge amount of research efforts brought into how we can actually make novel batteries with better densities. There are, however, several key scientific challenges. I go into these in greater detail in the reports, and these are some of these apply greater to some of these chemistries than others. But the first is reversibility. How do you ensure that the actual battery reaction proceeds both ways with similar efficiency? So lithium sulfur especially has a issue where the reversibility reaction due to secondary reactions is not as good as it could be, and that leads to the second degradation. Basically, if you have issues with reversibility, you have issues with the amount of charge cycles you can get before the battery basically breaks down due to the effects of secondary reactions degrading the cell, either damaging the electrolyte or the electrodes themselves. And the third is also instability, the actual stability of the electrolyte itself as a chemical mixture, and also the electrodes themselves degrading over time due to basically the fact that they are relatively unstable chemicals. So I said the UK has got several large R&D people looking at this, but large-scale commercialization is mainly taking place. Efforts may take place in the Far East. I think Toyota is almost leading on the solid-state batteries. Solid-state batteries have a specific issue that the electrode itself, the electrolyte itself, needs to be solid-state, and therefore you need very interesting and difficult to replicate chemistry in order to make it work. Large-scale commercialization for new battery chemistries is expected to be at least a decade away, because a lot of these are problems still in the basic R&D stages, actually the chemistry of the battery itself, rather than the actual scale up at this point. So once we've actually worked out those basic sort of chemical issues and made a reversible, sustainable battery, then we can commercialize it. But saying that, especially with solid state batteries, there may well be smaller sort of rollouts of high value markets, so high end electric vehicles and aircraft. But these may be more what we call late stage demonstrations than actual large scale commercializations. So moving on swiftly to hydrogen. Sorry about the size of this slide, but basically trying to fit everything onto a slide. Hydrogen is obviously can be used as an energy carrier. We've had a fair amount about it in the news recently. And basically, if you're going to use hydrogen successfully, you want to substitute it for oil and gas in sections of the system where electrification is difficult or expensive. So large scale industry, maybe aviation, maybe stuff like HGV vehicles, basically areas where electrification may not be as sensible as in other areas. So that's where you want to use hydrogen. But it's obviously not itself a primary fuel. It needs to be produced prior to use, and therefore you have efficiency issues where you lose a fair amount of energy converting hydrogen to and from electricity. In terms of actual low carbon net zero usage, electrolysis of hydrogen for water with low carbon electricity is probably the way to go. So there's two ways you can do this. You can either do it at low temperature electrolysis, and this is at ambient temperature or maybe a bit above, or you can do it at higher temperatures, sort of about 700 degrees centigrade and so on, at which point the reaction is a lot more efficient, but obviously you need a fair amount of heat input in order to get to that level. So electrolysis is basically, there's a couple of cell technologies. Alkaline water electrolysis, which is the older technology, and the more efficient and effective protein exchange membrane electrolysis, but it's a less mature technology, that one, and requires a fair amount of work looking at replacing both precious metal catalysts, platinum catalysts, lower cost substitutes, and also improving cell lifetimes. At higher temperatures, we have solid oxide fuel cells. They're the dominant technology. These once again are in sort of pre-commercialization stage, and there are at least one major UK startup looking at this, as well as a fair amount of Korean and Japanese companies. Materials challenges once again here are durability and performance. These are later stage materials challenges, as in contrast to battery technology. And it's basically about getting up to techniques to manufacture at scale, and once again, everyone's favorite bugbear, standardized testing to ensure the materials can hold up over long standard use cycles. Another energy carrier talked about is ammonia. We use ammonia heavily in fertilizer. About 1% of global energy consumption goes into the Haber-Bosch process to make ammonia for fertilizer. So we make a lot of it, and it's very energy intensive to make, but it does have several advantages as an energy carrier as compared to hydrogen. It's easy to transport, it's got high energy density. We already have a mature storage transportation infrastructure available for it, and it also burns cleanly, so you just get nitrogen, water, and oxygen out of it. But once again, at the moment, you need to convert to hydrogen and then to ammonia, so you get more and more efficiency losses. So really, ammonia for energy consumption purposes, you really want to use it either for applications which are probably more remote, where you need to store energy for longer periods of time or transported longer distances. So yeah, ammonia is traditionally made use a Haber-Bosch process, which is extremely energy intensive. At the moment, there is some early work looking at how we can make ammonia in a more sustainable way. There's some research groups looking at the idea of hydrogen electrolysis coupled with the Haber-Bosch process, basically one facility powered by low carbon electricity. Now, you have intermittent operation because of the way the system works. So you need to deal with better catalysts and also overcoming these low efficiencies at smaller scales, because the idea that this would be more localized ammonia production instead of in larger facilities, basically used closer to the wind farm, as it were. There's also early work on direct electrochemical synthesis of ammonia. This has been demonstrated in the lab, but it's a lot less efficient currently than the Haber-Bosch process. So there's significant basic optimization work would need to be carried out on improving catalysis efficiency and also cell material efficiency. So this is a lot earlier, I think, but there is maybe some niche products and purposes in which ammonia could be useful as an energy carrier. Okay, sorry for zooming through that so quickly, but this is the final part of the presentation, some research and policy recommendations. So we hosted a research workshop last year from the UK with the UK academic and industrial sectors in the materials energy R&D space. So basically, we wanted to understand the strengths of the UK's novel materials sector for R&D capabilities, what the challenges are, and the policy decisions which need to be made to support researchers and commercializers. So this is talked about more in the report, but I'll just go through the major recommendations that came out of that workshop. So first of all, testing and standardization, as I talked about earlier. The UK is definitely missing dedicated resources for testing, degradation testing, benchmarking, standardization, certification. This is kind of a sort of key central facility, and it would be useful, as I said, for PV, for batteries, for hydrogen, for other areas, if we had resources in order to basically show that these materials, how these materials worked in the real world, and whether they'd be suitable for further commercialization without needing to go offshore. Technology transfer as well. The UK has a big issue with this. Basically, companies and academia need to be better at working together to transfer research and development up the chain. So the one thing that came up from the industry partners is that it was often difficult to get open access to reports, articles, and data sets. I think this is improving a bit, but it still needs to be improved some more. And also, universities need to maybe consider the value of long-term relationships as well as short-term IP valuation. This came up a couple of times. Universities were interested in charging a relatively high price for their IP, which often pushed out smaller companies, which could work with universities over longer periods of time. Thirdly, commercialization incentives. We've basically got a very good basic materials R&D sector in the UK, but the incentives to actually push forward these into commercialized products are few in other countries. So greater incentives could assist it. So greater access to venture capital support, which actually works well. Easy access to test beds, demonstration platforms, as seen in the first section, and basically further tax incentives for innovation and applied R&D. So basically incentivizing people to actually bring these forward and develop them in the UK instead of offshore. Fourth is speculative research. Obviously, this is for academics, so they like the idea of money. But the point was made several times that materials is a field that's basically benefits heavily from blue sky research. Sometimes material properties can be non-intuitive. Breakthroughs can come from really strange areas. We should not be afraid to actually fund research in this area which isn't actually necessarily directly related to something else, because it could well lead to disruptive impact. Obviously, this needs to be gone through the standard research commissioning process, but it should be funded with fewer concerns about immediate results or necessarily like immediately impact in a specific area. And for lastly, research continuity. I think this is a problem across academia as a whole, but because of materials requires, as well as researchers, it requires technical support staff, it requires labs to be maintained. It should be, if you have a successful team, you need to be able to keep them together over long periods of time, because that's how good teamwork works. And they should be able to be supported to kept together after the end for grant by providing a measure of continuity funding as they move on to the next big project. And yeah, we need to make sure that we have a pipeline of researchers coming up and they're good quality. So funding needs to be pushed towards early career researchers to be able to, and expanded in that area to ensure that we basically have a good quality research pipeline of researchers for the future. As I said, there's more in the report about challenges and incentives. Right, so that is the end of my section. Sorry for the speed I had to run through that. There's a fair amount in there. The report itself will be coming out later on this, hopefully later on this month or early next month, at a full launch event hosted by the Energy Futures Lab at Imperial. We will ensure that people in the UKERC newsletters are kept abreast at this and provide you links to both download the report and also to join the launch events. Apart from that, I believe there's also a feedback thing to fill out for this particular webinar, and they're asking me to say, which you can find on the chat. And that's the end of my section. And just have you got any further questions before we end? Thank you.